So up to now we've been looking at some of the very elementary functions available in Matlab to perform some simple tasks, but it's time now to start looking at some of the more powerful features available to us. And in preparation for that, first let's cover quickly 6 simple functions. The first being the I function, which creates for us an identity matrix. So here's your matrix with and because we've issued the statement I4 here, that's created for us a 4 by 4 matrix, and you can see zeros everywhere except along the diagonal. So that's for us the identity matrix. And if we instead wanted to populate our matrix with ones, then we could just issue the statement ones for, and we've got here the 4 by 4 that's filled with ones. And similarly, if we wanted the zeros, then that's zeros. The zeros command does exist. And of course, we could shape this however we'd like. So if we issued the statement I 4, 5, then you can see here there's an extra column. And of course, the identity matrix, this is effectively an identity matrix with the 5th row missing here. So that does exist. Of course, we might have a question about how useful that would be, but anyway, that's what's possible. And so ones, I, and zeros can be used to create our special types of matrices quite quickly and easily. Then let's, for the sake of completeness, we did talk about the rand function before, and we said rand with that argument would create for us a matrix of that dimension and populated with random numbers. So we have that, and of course the same applies. We can ask for rand 3, 4, or we could make this a vector. That's all possible. So let's create now the matrix A, and let's fill that with random numbers. And let's ask here for the upper triangle for that matrix. So if we write in the statement try upper, TRIU, of that matrix, then that's going to give us the upper triangle on that matrix. So if you compare these two, you can see in the space up here, we've got the same values as down here, and so that try upper has successfully given us the upper triangle. It substituted zeros for the values down here. Right, so that's the upper triangle, and if we ask for the lower triangle, which we get just by issuing TRIL, so try lower, then that's the lower triangle of matrix A. So just pulling matrix A up again, you can see here this is the lower triangle of matrix A. Right, so that's try upper, try lower. So that's just for quickly creating our matrices. Let's look now at our first important operation, which is the matrix inversion. So the statement INVA returns for us the inverse of the matrix A. And let's just test to see whether that is actually an inverse matrix. So we can ask for A times INVA, and we see here the result of that is indeed the identity matrix. Right, you can see a diagonal of ones and the rest are zeros. So this appears to be giving us the inverse of matrix A. So that's INVA. And of course we know that if we have any two of these rows that are the same, then this matrix is singular and cannot be inverted. So let's just check to see what the compiler says to us if we have two rows being the same. And to check that, let's just set the first row to be equal to the second one. And remember, the first dimension is the row number, so we want the first row, and we want all the elements along the column, right? So that's what we do there. First row, all elements, right? The colon, remember. And let's set that to be the same as the second row. So we pick out second row, all elements along that second row, and let's do that. So you can see now the first 2 rows are the same. And if we ask for the inverse of this, you see here the compiler complains that the matrix is singular to working precision. So it is correctly warning us about this. Right, so that's matrix inversion. Now let's look at some of the operators involving matrix inversion. So we have here the left divide or backslash operator, and this operator is effectively, it says here in the notes, it's the matrix division of B into A. So if we write it like this, A backslash B, then this is A into B, and so that's the same as saying inverse of A multiplied with B. And let's just test to see that that does give us the same result. So let's test to see if that gives us the right results. Let's say here A is rand. Let's recreate matrix A, and that's there. Let's recreate matrix B. So that's going to give us different random numbers. And so let's look at the inverse of A multiplied with B. Right, so that's the result of that. And then let's look at using the backslash operator on that. So looking here, it's A backslash B, so that's the orientation for a backslash, right? So let's go A backslash B, and you can see a similar result to when we issued the inverse of A times B. So that seems to be giving us the same result here, and we can check that by subtracting those two matrices. So INVA times B minus A backslash B, right? And you see a matrix filled with numbers that are extremely small. These are all very close to zero. In other words, these are giving us virtually the same result there. So this backslash operator is operating in the way that we expect. So that's the backslash operator, and then let's look at the right divide on the other hand. So here the forward slash, it looks like this. So that's the orientation for the forward slash, which is the right matrix divide, which is the same as matrix division of B into A, which is effectively A times the inverse of matrix B. So let's check that one. So A times inverse of B, right, is that, and the summary operator is A forward slash B, like that, and you can see similar results there. And again, let's look at this in the residual. So A forward slash B minus A times the inverse of B, and you see the result there. These numbers are extremely small, 10 to the power minus 15. So this is giving us, these two are extremely close. So A forward slash B is giving us very similar numbers to A times the inverse of B. So that's the back and forward slash operator. Right, then we also have available to us the matrix powers. So let's say we have, well, we can just use matrix A again. And if we wanted the square of this matrix, A squared, right, that's the result we'd get. And we can just check that one. So if we issue the statement A times A, we can see we get the same result as for A squared. So again, we can just check that A times A minus A squared, right, and that's perfectly the same. So we can calculate matrices raised to arbitrary powers there, and we aren't stuck to integers, right? If you know your linear algebra, you know that you can compute the A raised to any power. So if we were to write A to the 0.5, then we find that the interpreter, well, that the results are available to us. So A raised to a power, that's the vector matrix power. Right, now let's look at one of the more powerful functions in Matlab, namely the one that gives us eigenvectors and eigenvalues. So the statement I does that for us, and just to recap, we recall that the eigenvectors and eigenvalues are numbers or objects such that this holds. Right? If we have some matrix A, then there may exist some vector V and some scalar lambda such that this holds.